The silence before. Perihelion, the enigma of 3. Atlas. Far beyond the noise of Earth, the third interstellar visitor, officially designated 3 Atlas, 3ATLS, drifts toward Mars. Only days remain before its passage brings it so close to the red planet that every major space agency should, by all rights, be on high alert. Instead, the channels go dark. Mission livestreams fall silent. Official voices disappear. The object's path cuts almost perfectly flat through the plane of the solar system, a maneuver no natural comet should be capable of. With its confirmed trajectory, a corridor only 5 degrees from the solar plane, and a hyperbolic inbound velocity of 58 km/s, it slices through our planetary neighborhood as if following a pre-written flight plan. Yet the institutions that should be watching remain mute. Why have the telescopes gone quiet, just as 3 Atlas races toward Mars? And what if the truth is more extraordinary and more unsettling than anyone dares to say? A growing quiet. As the object closes in, the silence deepens. Mars, red and mute in the dark, drifts a mere 18 million miles from the predicted path of 3 Atlas, close enough for orbiting probes to capture every flicker of light, if anyone were looking. But the official data streams from Mars Express and Trace Gas Orbiter remain nearly empty. No press releases, no mission updates. The normally open flow of raw data, once eager to showcase every Martian dust storm or frost cycle, now shows only routine science. No mention of the interstellar visitor slicing through their skies. Inside mission planning rooms, however, something is moving. Observation schedules are quietly rewritten. Spectrometers retuned for water, ice, organic compounds, and isotopic signatures. Each alteration is subtle, a time window shifted here, an exposure added there, but taken together, they form a pattern, a coordinated global response cloaked in silence. Only hints leak through technical logs, time-stamped notes, or updates to instrument targets, while the world's attention stays focused elsewhere. The window of close passage is measured in days, not weeks. Its coma and tail are faint but visible to any telescope aimed correctly. For comparison, the last interstellar object, Borisov, never came closer than 150 million miles to any planet. 3. Atlas, in contrast, will graze within a fraction of that distance. Its geometry is eerily flat and precise, so precise that orbital analysts have begun calling it mission-like. Still, the silence holds. Discovery. It began quietly on July 1, 2025, during a cold night in Chile's southern skies. The Atlas Survey telescope detected a fast-moving point of light that matched no known solar system trajectory. Within hours, orbital analysts across the world were alerted. By dawn, the Minor Planet Center logged the first astrometric data, and teams began scouring archives for earlier traces. They found them, faint tracks buried in Zwicky Transient Facility images from June 14th, hiding in plain sight. Each new data point refined the orbit. The numbers told a story that allowed for no doubt. This was an interstellar visitor. Within days, the orbital solution stabilized, eccentricity greater than 1, hyperbolic excess velocity 58 km/s, inclination less than 5 degrees to the ecliptic, unusually flat. Most interstellar objects plunge steeply through the solar system. This one skimmed its surface, threading through the orbits of Mars, Earth, Venus, and Jupiter, a narrow corridor that seemed deliberately chosen. Orbital dynamicists ran Monte Carlo ensembles, projecting its motion millions of years backward and forward. The verdict was unanimous. No previous link to the Sun, no Oort cloud origin, no gravitational capture. 3. Atlas entered from the galactic field, bound to nothing, and would never return. The odds of such a planar, multi-planet trajectory arising by chance? Less than 1 in 5,000, according to model statistics. An object that breathes. By the time it reached 6.4 astronomical units, 3 Atlas broke the rules again. Its brightness began to pulse. Water ice should not sublimate at that distance, yet photometric data from southern observatories showed rhythmic outbursts, rising and fading in a heartbeat pattern. Each pulse lasted hours to days, repeating unpredictably. No ordinary comet behaves like this. High-resolution imaging from Chile and South Africa revealed something stranger. Its tail curved toward the sun, not away. Standard models predict fine dust streaming outward under solar pressure, but this tail contained heavy, slow-moving grains, even clumps, sometimes bending forward. Spectral analysis confirmed it. The dust was too dense, too cohesive to behave normally. Some researchers invoked magnetic effects, others proposed internal vents or buried volatile pockets erupting in bursts, but no consensus formed. The comet seemed to breathe, each pulse a whisper of some deeper process. As 3 Atlas approached Jupiter's orbit, the ratio of dust to gas became abnormal. Mass estimates based on coma brightness suggested more material leaving the core than its size should allow. Perhaps it was larger, perhaps fragmenting, or perhaps something else. Behind closed doors, professional teams shifted into high gear. Telescopes worldwide entered enhanced monitoring mode. Mars Express updated its observation queue. Trace Gas Orbiter reprogrammed its spectrometers to scan for rare isotopes and organic compounds. Each modification appeared in internal bulletins, never in press releases. Even the James Webb Space Telescope allocated emergency hours to 3 Atlas between March and September. Instruments NIR-SPEC and MIRI were scheduled to probe its molecular signatures, pristine material preserved since its interstellar voyage. Review summaries, visible only in brief abstracts, called the event a unique astrophysical opportunity. Yet the final scheduling notice included a caveat: observation subject to solar conjunction constraints. Hubble followed with its own campaign, high-frequency imaging of the dense halo of dust and gas. Early findings hinted at a paradox. The total mass of expelled material far exceeded what a 6-kilometer nucleus could supply. Either the comet was far larger than believed, or some unseen mechanism was amplifying its outgassing. Then came the quiet embargo. Conference sessions closed, preprints stopped. Internal memos carried labels like operational security or internal review only. Slack channels once full of filter debates fell silent, replaced by coded messages and evasive jokes. A handful of leaks escaped, fragments of logs, redacted email chains mentioning a technical anomaly. Each was swiftly scrubbed. The official explanation: data held for coordinated release. But among the community, one feeling spread: unease. Science had gone quiet in a way it rarely does. Approaching the sun, by late October, the countdown to perihelion began. For ground-based observers, the view was about to vanish. The comet's angular separation from the sun dropped below 15 degrees. Too close, too bright. Hubble and Webb, bound by strict solar avoidance rules, shut down observations. Their once busy logs turned blank for nearly 2 weeks, October 29th to November 10th, 2025. Only Mars remained in position to watch. Its orbit trailed just 18 million miles behind the inbound path, an ideal vantage point. Controllers of Mars Express and Trace Gas Orbiter, operating in the shadows of institutional silence, scrambled to capture whatever data they could before solar interference cut contact. Every kilobyte mattered. Meanwhile, the SOHO and Stereo solar observatories prepared to catch a glimpse. Their coronagraphs, designed to block the sun's glare, might record the comet's approach indirectly, bright echoes against the plasma sea. But they could not reveal composition, only brightness. For the first time since its discovery, the story of 3rd Atlas continued beyond the reach of Earth's instruments. All the world could do was wait. October 31st, 2025. Perihelion. Months of speculation came down to one question: how large was the heart of 3 Atlas? Early Hubble and Webb images suggested a nucleus less than 6 kilometers across. But as it neared Mars, photometric models demanded something larger, perhaps 10 kilometers in diameter, a giant among interstellar travelers. If true, it would rival the largest long-period comets ever observed and reshape theories of interstellar object formation. 3 scenarios dominated discussion behind closed doors. Fragmentation: the nucleus would shatter, scattering debris along its path. Outburst: a violent ejection of gas and dust, releasing its secrets in a single explosive act. Survival: the object would endure intact, emerging from perihelion unchanged. The last option raised the most unsettling implications. If 3 Atlas survived, maintaining its low inclination, mission-like trajectory, the question of intent would linger. Was it natural or was it engineered? Official teams leaned toward the natural hypothesis, an unusually volatile-rich interstellar comet, its strange behavior the product of buried ices and alien chemistry. But a vocal minority whispered about mission profiles, about its corridor-like orbit and rhythmic outbursts. When Earth's telescopes blinked out behind the sun, only Mars and the solar observatories remained to witness the climax. No one outside a handful of control rooms knew what the instruments saw. Aftermath. By November, the light curve flattened, the signals faded, and the data pipelines reopened, cautiously. Official statements were sparse. The comet had survived, some said. Others claimed it had disintegrated. No high-resolution images were released. What 3 Atlas truly was, a natural wanderer or something else entirely, remains buried in encrypted archives, waiting for future historians to decode. One fact, however, endures beyond debate. 3 Atlas defied the known laws of cometary science and exposed the deep vulnerabilities in how human institutions communicate extraordinary data. Somewhere between the stars and the silence, the third visitor slipped past the sun and left behind more questions than any telescope could answer.